So thank you for joining our presentation. In this talk, Paul and I will present how we have exploited the Rowhammer bug to authenticate on a victim VM from a co-hosted attacker VM by flipping a single bit. Before we start, a few words about who we are. I'm Mehdi Talbi, security researcher at Stormshield, where I have mainly worked on the ACAD security project. I came from academia. I have a PhD followed by postdoc and blah, blah, blah. And I'm mainly interested in advanced exploitation techniques, abusing virtual machines. For example, Paul and I have wrote the paper in FRAC about escaping from a virtual machine. And I'm in general interested in anything related to low-level stuff.
Okay, hi, I'm Paul. I'm pretty the same interest as Mehdi, except for the boring postdoc stuff. And I also work at Stormshield. And that's it.
Yeah. So before giving the agenda, I want to present the context or the attack that we have mounted. So here we assume two virtual machines, the attacker VM and the victim VM. And the goal here is to try to authenticate on the victim VM without knowing the password of the victim VM, obviously, and without exploiting any software bug present in the victim VM. And in this presentation, we'll show how we have exploited the Rowhammer bug to flip a bit in the PAM Unix module loaded in the victim VM so that we can authenticate later with a blank or wrong password. So here I have a little teaser about about the demo that we will show at the end of this presentation. That's one. Wow. Ah, sorry.
It's a Mac. It's not easy to use.
Okay. So here I will try to authenticate on the victim VM with the password Infiltrate, and the first attempt will fail. And then we'll run from the attacker VM the exploit running an instance of Rowhammer, and then try to authenticate again with the same password, and we succeed in authenticating.
Okay.
Back to the slide. So here is the agenda. So I think that many of you have already heard about the Rowhammer bug. Here we will focus on how to Rowhammer from a virtual machine. And then we'll present one feature of modern operating system, memory deduplication, and how we can abuse this feature to flip bits in memory in a controlled way. Then we'll present our attack on the libpam and how we can generalize the technique that we used to attack other binaries. Basically, given a program P, how we can automatically find all bits in that program P that, if flipped, can change the outcome of this program. And finally, we'll conclude with some remarks on how we can improve this work. Okay, let's start with Rowhammering. Here I'll try to explain the root cause of the bug. So a DRAM chip consists of rows of memory cells. This is not totally true, but let's assume that for now. And these memory cells are periodically refreshed. And then when the CPU requests a read or write operation on one byte of memory, the data is transferred from the row in physical memory to what we call the row buffer. And then and this operation is called discharging. And then after some amount of time, the data is copied back from the row buffer to the original row. And this operation is called recharging. And the whole process of discharging and recharging is called row activation. And frequent row activation can cause disturbance error that are reflected by a higher discharge rate on adjacent memory cells. And this could lead to bit flips in adjacent memory cells if they are not refreshed before they lose their charge. And it's basically a hardware bug. So, and the snippet of code is sufficient to produce bit flips in memory. So here we are alternating the reading from two memory addresses, X and Y, And this is required, otherwise we'll be served from the row buffer, and we won't be able to activate a row repeatedly. And we need also to flush these addresses, otherwise we'll be served from the cache. And Mark Seaborn and Halvar Flake have noticed that the effect of the row hammer bug is amplified on the victim row key if we hammer its neighbor, the row key -1 and the row key +1. And this technique is called a double-sided row hammering. Okay, now all the story of the row hammer bug starts with Kim's paper in 2014, flipping bits in memory without accessing them. Kim and Al have noticed that frequent row activation can cause bit flips in memory. And then Halvar Flake and Mark Seaborn were the first to exploit the row hammer bug to gain kernel privileges. In one of their exploits, they managed to get a read-write access to the whole physical memory. And the basic idea was to spray the physical memory with many page tables, so that if we run an instance of row hammering, there is a high chance to flip a bit in page table entry. And then we have the paper from Eric Bosman and Al from VSEC Research Security Team. Eric Bosman and Al succeeded in running an instance of row hammering from JavaScript running inside a fully patched Edge browser, and they managed to get a read-write access to the memory of the browser. And then the same researcher from VSEC Research Security Team have presented a new technique called flip feng shui. And they really pushed the exploitation of the row hammer bug to the next level. They combined the exploitation of the row hammer bug with an abuse of the memory deduplication feature. And in their attack scenario, they were able to run an instance of row hammering from the attacker VM to flip bits in sensitive loaded file in the victim VM, assuming they know the content of this sensitive file. And in their attack, they targeted the known host file, and by weakening RSA moduli in known host file, they were able to generate new private keys and authenticate on the victim VM. And here in this presentation, we are mounting a similar attack, but except of modifying the content of some sensitive file, we choose to corrupt the state of some running binaries in the victim VM. And we also provide a set of tools to aid to find automatically interesting bits to flip. And finally, we have the drummer attack, a successful exploit of the row hammer bug to get root privileges on Android running on some ARM devices. Okay, before presenting how to row hammer from a virtual machine, I need to introduce some extra definitions. So here we have a memory module, and we can plug this memory module into a channel. And then a memory module is made of memory chips that could be present on both sides of the memory module, and each side is called a rank. Finally, a memory chip is made of banks, and the bank is simply a matrix of columns and rows of memory cells. And our testing lab machine has the following configuration. So we have 8 GB of RAM, we have a dual channel configuration, which means that we have one memory module per channel. Our memory modules have memory chips on both sides, so we have 2 ranks per memory module. Then each side has 8 memory chips, and a memory chip is made of 8 banks, and finally a bank is made of 2 power 15 rows and 2 power 10 columns. And we can simply compute the total size of the available memory by multiplying the number of modules, ranks, chips, banks, and so on. And now, when the CPU requests a read or write operation on 1 byte of memory, the memory controller is in charge of fulfilling this request. And the memory controller will use the physical address to select the channel, the bank, the rank, the row, and so on. And Mark Seaborn has identified this mapping for Santi Bridge, and this mapping matches with the configuration I gave in the previous slide. So in this mapping, we have bits 0 to 5 that are the lower 6 bit of byte and text within a row. Then we have bit 6 to select the channel. Then we have bits 7 to 13 that are the higher 7 bits of byte and text within a row. Then we have bits 14 to 16 to get the number of the bank, but not exactly, because to get the number of the bank, we have to XOR bits 14 to 16 to the 3 LSB row bits, which means that to get the number of the bank, we have to XOR bits 14 to 16 to bits 18 to 20. Then the bit 17 allows to select the rank, and the rest of the bits allow to select the row. Oh. Okay. Okay, now we are ready to row hammer from a virtual machine. Okay, row hammering requires to select a pair of addresses that belong to the same bank. And assuming we know the underlying physical mapping, how we can select a pair of addresses that map to the same bank but to different rows. And the fact that we are row hammering from a virtual machine limits the available option. For example, we don't have access to the page map file, so we cannot convert a virtual address into a physical one. So there is only one option left for us. We will rely on transparent to huge pages. Transparent to huge pages, or THP for short, is a kernel thread running on the background where a kernel thread running on the background attempts to allocate huge pages of 2 megabyte size. And since a huge page cover multiple rows, 8 exactly, we can this way navigate through rows. So how this works? So in the guest, we'll allocate a large buffer aligned on 2 megabyte boundary. Then after some amount of time, the kernel thread running on the guest will try to back our large buffer in the guest with huge pages. And the same goes for the kernel thread running this time on the host, where the QEMU virtual address space will be backed also by huge pages. So this way we can get our large buffer in the guest backed with huge pages in physical memory. Okay, one last slide, row selection. I had this slide, but it's necessary. Remember that row hammering requires to select a pair. Remember that we want to perform double-sided row hammering. So, and thanks to huge page, we can now select one address from. We can now pick one address from row I and another one from row I plus 2, such that they belong to the same channel and the same rank. But how about banks? The XORing scheme in the address mapping makes it a little bit challenging to select a pair of addresses that belong to the same bank. And actually we can't. We can simply reduce the number of matching banks. So to illustrate that, let's BI1 to BI3, the bits identifying a bank in row I. And let's BG1 to BG3, the bits identifying a bank in row G. Now, if we pick an address from row I, we know that it will share the same LSB row bit in row G, because G is equal to I plus 2, and this arithmetic operation will preserve the LSB row bit. This bit is represented with the red box in this figure. So given that, we can deduce that two addresses belong to the same bank only if the bit BI3 is equal to the bit BG3, and only if the bit BI1, BI2 are different from BG1, BG2. So that if now we pick an address from row I, only 3 addresses out of 8 satisfies this condition. And this will allow us to optimize the row hammering process, because we can row hammer the address from row I and the 3 matching address in row I plus 2 in one go.
Okay, so Mehdi just told you how we can flip a bit in our own memory, but recall that the goal is to flip a bit in the victim VM. So we will have to abuse a feature called memory deduplication. So what is memory deduplication? Memory deduplication is a feature of modern operating systems that tries to reduce memory footprints. It's especially efficient on virtual machine because when you have lots of virtual machines on the same host, yeah, there is a lot of chance that they share the same kernel, same libs, etc. So the goal of the kernel of the host is to take 2 pages from 2 processes or 2 virtual machines and to back them with the same physical page. So on the left of the screen you have the state before the merge, so there is 2 green pages that share the same content. They are backed by 2 different pages on the physical memory, and after memory deduplication they share the same memory. Okay, here we have to take some level and recall the different attack steps before we go deeper into memory deduplication. So, as I said, our goal is to modify bits in a file. In our case, it's PAM Unix SO, and this file is hosted in the victim VM. And for now, we assume that we know its content, but we will see later that we can guess its content. Okay, and there is one thing that Mehdi don't tell you is that raw hammering is reproducible. Once you know how to flip a given bit, you will be able to flip it again by doing the raw hammer step you have done before. So, first step of the attack, you have to map the available physical memory using THP, like Mehdi said. Then you will try to hammer the whole memory. So this is a quite long step because you are hammering huge pages, and in your test sample it would take between a few minutes to up to 1 hour or more. But as long as you are doing that, the victim VM don't know what you are doing because you don't touch the victim VM. So the only effect you have is heavy load on read-write operation. Once you have found interesting flippable bits, you just have to load the target file in your memory and ensure that the same file is loaded in the victim VM. Then you have to wait, so this is the green square on the screen, and then you have to wait for memory deduplication, and you have to ensure that the victim memory will link to your memory, so you can do the raw hammering again. Then you hammer, and then you enjoy free connection to the victim VM. So how can we do that? I will focus on kernel same page merging. It's memory deduplication on Linux. So as on other operating systems, KSM aims at reducing memory footprints. And to do that, it will scan the memory looking for pages with identical content. It will do it periodically. And for example, in a sample configuration, it will scan 100 pages every 20 milliseconds. Once it finds 2 pages with the same content, and if the pages have the flag Mehdi mergeable set, it will merge the 2 pages, so they will share the same physical page. And there is one thing important to know about KSM, is how it handles writing to a merge page. So obviously you can just write to a page that has been merged and hope that the thing you write will go into the other VM. So to handle that, KSM will trigger a page fault, and then KSM will unmerge the pages and apply your write operation. We have to dig a little more into KSM internals because there is a few outcomes that we have to bypass when trying to implement the rammer. So how KSM works internally, it maintains 2 red-black trees. The first one is called the stable tree. The stable tree keeps track of all the shared pages. So every time KSM found 2 or more pages that are mergeable, they will go into the stable tree. And KSM maintains a second red-black tree called the unstable tree. Okay? The unstable tree will store all the pages that are candidates for merging. This is important because the unstable tree is trashed and reconstructed after a complete scan. So the stable tree will stay as long as the VM, as the host is up, but the unstable tree will be trashed regularly. And more important, KSM always tries to merge pages from the stable tree and then from the unstable tree. So this is important because of one outcome you have to bypass. It's called winning the merge. So the question is, how can we guarantee that KSM will back merge pages by the physical page controlled by the attacker? And to do that, there is two options. One option that is obvious, but not realistic. It's starting the attacker VM before the victim VM. So KSM will keep the page that he has registered before in the unstable tree. And when the victim VM will load, it will just merge it with the page you had in your VM. But obviously, you can't assume that you will control when a victim VM is boot because it's too strange. So the realistic option applies to load 2 copies of the target file in the attacker VM. So that way you ensure that your 2 copies are merged first. If they are merged, they go to the stable tree, and once the copy that is in the victim VM will be loaded, it will be merged into the stable tree, so into your copy. Okay, there is a second outcome that we have to handle. It's KSM versus THP. So recall that THP is a thread that tries to merge 4 kilobit pages to form huge pages. Okay, but KSM will try to do another thing, that is merges 4 kilobit pages sharing the same content. And the issue might be that KSM could break the huge pages that we allocated on the first stage of the attack. So the solution is quite simple. We just have to add some entropy to memory pages. So for example, in our test, we fill the top of every 4 kilobit pages with 8 random bytes. This way KSM won't work on the huge page you allocated. And you can try to rehammer it. Okay, now I will let Mehdi talk to you about putting the lip lamp.
Okay, now we know how to row hammer from a virtual machine and how to flip bits in memory in a controlled way. Here we will focus on the target, and in our case the target is the LibPAM. More precisely, given an instance of the LibPAM running on the victim VM or any program P running on the victim VM, how one can find interesting bits to flip in that program P that can change the outcome of the program if the bits are flipped. So in our exploit, we targeted the LibPAM because it provides authentication mechanism on widely deployed Unix system. And we have identified 2 interesting functions. The first one is PAM-FM authenticate, which performs the main task of authenticating a user. And the second function is Unix blank password, which checks if the user does not have a blank password. So now the question is, given the instance of the LibPAM or any program P running on the victim VM, how we can find all bits in that program P that can change the program if the bits are flipped. Doing it manually is very painful, and we can for sure miss some interesting bits to flip. So the basic idea here was to rely on timeless debugging capabilities. So the idea is to break on the desired function and save a trace session. Then for each bit in that function, we flip the bit, run the function until it returns, and then check whether the flipped bit changes the expected result of that function. And then proceed with the second bit and so on until we have covered the code of that function. So we have implemented a Python script that relies on timeless debugging capabilities of Radar 2, and the script is not perfect. Sometimes it crashes, but it's not a problem. We can just restart the script again by skipping the instruction that caused the crash. So we run this script on the PAM Unix module, and mainly on the 2 functions that I presented in the previous slide. And we found 17-bit flips in the PAM Unix module that, if flipped, could allow one to authenticate on the victim VM with a blank or wrong password. For example, we can play with conditional branches The fun fact here is that there is only a distance of harming of 1 between the jump equal instruction or the jump not equal and the jump over instruction. Sometimes the flipped bit changes the operand of the instruction, which in some cases is sufficient to change the outcome of the authentication functions. For example, we can change the test EIX instruction with an exchange instruction, and so on.
So now we have all the steps required to do the full attack. So we will go over each step once again, and then we'll try to show you a demo. So recall that the first step is to allocate the available physical memory. To do that, we rely on THP. Then we add some entropy to memory pages to prevent KSM from breaking out THP pages. After that, we will try, so this is the EV and long step, that we can do this attack on .2 on, because obviously it's too long. So we hammer each pair of aggressor in rows in every huge page and check if we have bit flips in the victim row, and we check does this flip is interesting regards to our target. Once we found a good bit flip, we just load PAM Unix ISO module in the victim page in the attacker VM. Then we ensure PAM Unix ISO is loaded into the victim VM. So this is quite easy. You just have to try to maybe SSH on the victim VM once with the wrong password. So this will force PAM Unix load. You have to wait for KSM to merge the pages. So this is quite quick. In our test, it takes an average of 5 minutes. So you just have to wait. We will see later that we have some tools in order to detect that KSM has merged the pages. Once you are sure, or once you have waited long enough, you just have to hammer again. So this is quick, and then you just enjoy. So I will try the demo. Yep. Okay, on the wrong screen. D'accord. Comment on full screen là-dessus? Là. Cool. Okay. So here we are on the PAM Unix SO. We'll go into the PAM SM authenticate function. So we'll mimic what we could have done manually in order to find the flippable bits. So we can see that there is a PAM get user function that could be interesting. We can see the Unix blunt password that could be interesting too. And after the Unix blunt password, there is 2 instructions interesting, test and jump equal, that could be flippable into an exchange and jump not equal. So this is a quick version in real use case. It's quite longer to find those bits, and the idea is to run the Python script in order to get the flippable bits easily. So here we run flipflop.py on the trace from radar 2 on pamunix.so, given the offset of the interesting functions on lib pam sm authenticate. We skip one offset that is problematic. We skip the output, and we let radar, the script will flip some bits and try to find. So here we can see that it found at least 3 interesting instructions that could be flipped. So the first one is the test EAX that is flippable with 1 bit. The jump equal could be flipped in 4 ways. And we can see here that it's exactly the instruction that we had here. So the test EAX and the get out and the jump equal here. So now we have, from this script, we have an output that is a list of the interesting offsets. So all this can be done outside the VM, obviously, as long as you have the correct version of the PAM Unix SO. And next, we are going to the attacker VM. So we do SSH. We have the password, obviously. So here we will run the PoonPam or binary. So it will take the target, the PAM-Unix SO, in order to be able to load it in memory. The last argument is the offset file that we get from the previous tool. And the first step, mapping buffer, is the huge page. Next step is filling with some random in order to avoid THP to be broken by KSM. So here is the fun step. We are hammering, so this is obviously accelerated because it's quite long. And in red, we can see that the offsets that we found with the previous tool, and that's the offset we are interested in it. And in green, it's the offset we have found to be flippable, but we don't care. So we wait. I'll let you wait because I've waited a long time in front of the screen. You pray. Maybe you can kill a chicken. Yeah, we found flippable bit at the right offset. So now we have to ensure that the PAM-Unix SO file is loaded into the VM victim memory. So we will just try to SSH. It's also useful because we can show you that we don't have the password, so infiltrate don't work. Now we wait for KSM to merge the pages, and once it's okay, we just run the hammering again. The hammering is quick, and we try again SSH, and so I used to clap also in front of my screen when I get out again.
C'est là que tu parles.
C'est là?
Non.
Non, c'est là.
C'est côté-ci.
I'm lost. Okay, good.
C'est à toi.
To demo. Okay, so going further. Now that we successfully have a rammer that gives us access to the victim VM, there is a few things that could be enhanced. First, recall that when we try to write on a merge page, it triggers a page fault. And the page fault will be handled by the kernel, and the kernel will do a copy and write in order to unmerge the pages. And this is interesting because there is a noticeable difference in time between writing to a duplicated page and writing to an unshared page. We could leverage this in order to exploit a side channel timing attack in KSM. So we could use that to detect when two pages are merged. So it is interesting in order to don't wait 10 minutes and don't know if KSM has gone over the pages you want to merge. And this is also useful because recall that we assume that we know the version of the libpam that is in the victim VM. And we could know, for example, that the victim VM is a Debian, and we could try to download all the versions of the libpam in archive.debian.org, for example, load them into the attacker VM, and just try to wait a little bit, maybe detect when the pages are merged, and try to write on each version of the libpam. And if there is a noticeable difference in time writing in one specific version, then you know that this version might be used by another VM on the same host. So to do that, there is a Kane attack. Kane attack was discovered by Antonio Baresi et al. It consists of a few steps. So first, you allocate large buffer on n elements. So each buffer is 4 kilobytes. You fill the buffer with random, and then you copy each even element on the first half in its corresponding index on the second half of the buffer. So the green goes on the green, and the yellow on the yellow. You wait for KSM to go over all the pages, and then you just try to modify a byte into each element. And you will see, obviously, if KSM worked, that writing on the first elements will take much longer than writing on the element that has full random. So this way you can know the difference in time, and you can just play with the attack we told just before. So this is the main point that we could add to the attack in order to fully weaponize Rohammer on VM. A few words of conclusion. So the idea here was to have a successful Rohammer attack on a co-hosted virtual machine by corrupting the state of PAM-Unix SO module. Every tool we have are open source, so you can find it at this GitHub account. And yeah, the idea was to recall at least our team and our co-worker that Rohammer attacks are powerful and effective, and you have to take it in account. And there is only a few mitigation available currently, so ECC RAM obviously, and disabling KSM, but both mitigation are quite expensive. A few greets. We'd like to greet Pierre Sylvain, a colleague of us that have been really helpful. We'd like to thank Stormshield because they paid us while we were playing with Rohammer. And obviously Mark Seaborn, Alvar Flake, and Vusek, etc. who originally find this flow. And there is a few references, and if you have any question, we are open.
Thanks.
Thanks.
Well, people want questions or have questions? No, they just have questions. Here you go.
So with KSM, you said there's the mergeable pages, the mergeable flag is required for this, right?
Sorry, could you?
In KSM, you said that it requires the mergeable flag to be set on the pages, right? Is that pretty common?
Yeah.
Or is everything just mergeable, or is there anything that's not mergeable?
KSM has been designed for KVM. So, and KVM maps pages with this flag. So, yeah.
Okay. And when you disable KSM, is that just in the host OS or in all the guests also? Or
No,
just the
it's
host?
only on the host because the guest doesn't even know that KSM is working.
All right, thank you.
Lots?
You don't know when KSM ran, right? You just wait some amount of time and then guess that the pages have been merged. There's no way for you in the attacker VM to know that the merge happened, right?
We don't know if KSM is running, but we have way to check if he is running by allocating 2 pages with same content and just wait a long time, check if I write on it, is there a noticeable difference in time?
But when you write to it, then they're no longer merged. So didn't you kind of ruin the...
So you allocate 2 pages, you fill them with same contents, you allocate 2 pages with random content, you write on 1 pages, you count how long it takes, and you write on the pages that has random content, and if it takes longer on the page with same content, then you have KSM, and KSM has gone on it. And there is one point, you know that, and when you want to do the attack on the victim VM, you have to know if the KSM has gone over the page that you want to attack. And to do that, you have to know that KSM will scan the pages linearly. So you allocate pages with random, the pages that you want to attack, and the pages with the same content as the first. And if the 2 pages have been merged, then the one in between have been merged too.
Thank you.
Probably.
Probably.
Anyone else? Hi, so you said that the mergeable flag is usually set by applications like QEMU because that's what the flag is for. But for the KSM daemon to run, don't you actually also need to set the run sysctl or some file in sysfs that's normally disabled unless you don't have sysfs? So as far as I know, user space needs to explicitly enable this feature. Can you describe in which environments this feature is actually enabled by default, or are there cloud providers that turn it on, or in which context does KSM actually run in practice?
So if I understand correctly, because I'm not sure I heard it, your question is, are the feature we required to do the attack often enabled on the wild?
Yeah, I mean, because it's off by default, right?
Yeah, also our tests were on QEMU and KVM, and all the VMs that we use in our company have this configuration, so at least our company is vulnerable. And
okay. Yeah.
if you take a VM on non-hoster, they have surely activated KSM because it's huge performance gain in memory footprint and THP too. And this kind of attack could be done in different use cases. For example, I think Windows 10 use virtual machine to separate some critical processes from the user things, and Windows 10 also has a KSM-like feature, and it's enabled by default too. So you could try to do that on Windows 10. I don't know if I answered the right question or if I just told. No?
You good? Okay, we're good. All right.
You briefly mentioned quad-sided row hammer. Could you please explain that a bit more?
So could you repeat, please?
You talked about single-sided and double-sided row hammer, but I believe there was a slide on quad-sided row hammer.
Double side ou quad side? The quad side row hammer is just the fact that from a VM, we can't be sure that we are hammering from the two right row. So we have a guess to make. So we try to do the hammer from from 4 row over the victim row, because we don't know which one is the right. So we just hammer the 4 row once. I don't know if I'm clear.
The question is, what is the difference between the double-sided row hammering and the classic row hammering? Is that the question? Or?
No, between double-sided and quad-sided.
Okay. It's the same, just we optimize because we don't know which addresses belong to the same bank, so we row hammer the 4 matching addresses. So it's the same technique, but only two addresses will match.
Yeah, that's the slide.
Yeah.
That's the right slide. Because here we have, because of the XOR in the address scheme, you don't know which. Tell me if I'm wrong. Which bank you are? If the address you are selecting are in the right bank, so you have to ensure that BI3 is equal to BJ3, and BI1, BI2 is different than BJ1, BJ2, but it lets you with 4 rows, and you don't know, in these 4 rows there is 2 that are in the same bank and 2 that aren't in the same bank. So as you don't know, you just hammer the 4 row and don't care.
Thank you.
You mentioned the way to ensure that libpam is loaded was that you first did a failed authentication. Normally, wouldn't that happen in a fork off of the SSHD, and then that process actually dies? So I'm just wondering, for the second authentication, or how do you, if you could explain that a little?
So either the VM is not accessed a lot of time, so you have a chance that PAM Unix is unloaded from memory because the host is quite heavily loaded. Either you have to use the technique here's the solution 2. Option 2 here. You have to load two copies of PAM Unix SO on new attacker VM, and wait for KSM because I told that KSM has 2 trees, so the stable trees and the unstable trees. So maybe the PAM Unix SO and the victim VM will be in the unstable tree, but if you wait a full pass of KSM will trash the unstable tree. Then you load your 2 copies And as they are one right after the other, KSM will scan them linearly. It will see that they share the same content, so will merge them, put them in the stable tree, and when it scans the victim copy, it will just merge it back into from the stable tree. So you have to wait full KSM loop, load 2 copies on your VM, and the rest should be okay.
Cool. Thank you so much.